These stars would be the universe's first-ever stars, burning at scorching temperatures from pure hydrogen and helium, predating the creation of heavier elements by stars later on using nuclear fusion. These types of blazing primordial stars are nowhere to be found in the nearby universe, implying that they no longer exist. We can only glimpse them from light that is billions of years old, so they are special. The farthest source appears very compact, with colors suggesting it holds a stellar population largely devoid of heavy elements, possibly even containing population 3 stars. However, only Webb spectra will provide definitive answers. Distance estimates for these two galaxies rely on measuring their infrared colors. In the future, follow-up spectroscopy measurements showing how light stretches in the expanding universe will independently confirm these cosmic measurements. While we wait for these measurements, the JWST has been discovering even more intriguing things, such as dark stars. The JWST isn't only finding ancient galaxies. It's finding new and wondrous things every day. Scientists are astonished by the wild discoveries they're making through this device. One of these discoveries occurred in August 2023, when scientists believed they found something called dark stars. Dark stars were first theorized in 2007, and scientists are not even sure these stars actually exist. Dark stars are not powered by nuclear fusion but by the self-annihilation of dark matter, an invisible substance constituting 85% of the universe's matter. These candidate dark stars, while requiring further confirmation, could potentially rewrite our understanding of early star formation. Even though they are called dark stars, they're not the exact opposite of the giant balls of plasma we know. Ironically, dark stars could have emitted luminosity 1 billion times greater than the Sun and attained a mass 1 million times larger. Although never definitively observed, simulations suggest that they could have formed shortly after the Big Bang, originating from clouds of pure hydrogen and helium collapsing within protogalaxies rich in dark matter. In a report published in the Proceedings of the National Academy of Sciences USA, researchers proposed that at least 3 distant objects previously identified as galaxies by JWST might actually be single supermassive dark stars. These galaxies were part of the JWST's Advanced Deep Extragalactic Survey, also known as JADES. The objects in question were GSZ-13, GSZ-12, and GSZ-111. The discovery, if confirmed, would be groundbreaking. According to the co-author of the study, presently it cannot be definitively proven that these objects are dark stars, but their characteristics align with both dark stars and galaxies hosting fusion-powered stars. The technology of JWST holds the potential to resolve this uncertainty, with more observation time being the key requirement. Another co-author anticipates the hope of discovering one such dark star during JWST's operational lifetime. The origin of the universe's first stars presents 2 possibilities. The commonly held belief is that these early stars were fueled by nuclear fusion, much like modern stars. However, they would have been almost devoid of heavy elements beyond helium since such elements hadn't yet emerged in the early cosmos. These are the same as the population 3 stars we mentioned earlier. But there is another, more intriguing theory. In 2008, researcher F and her colleagues proposed a fascinating idea. They suggested that the universe's earliest stars might have drawn their energy from dark matter. This mysterious substance, which interacts solely through gravity, remains largely unknown in composition. In the early universe, dark stars could have emerged from collapsing clouds of helium and hydrogen formed during the Big Bang. Many theories suggest that dark matter particles possess the unique quality of being their own antiparticles. Antiparticles have the same mass but the opposite electric or magnetic properties of their given particle. For example, the antiparticle of an electron is a positron. It has the same mass as an electron but the exact opposite charge. When these two collide, they annihilate one another. If dark matter particles are their own antiparticles, their collisions will result in self-annihilations and particle decay. Their collisions within these collapsing clouds could have initiated a sequence of particle interactions, culminating in the creation of photons, electron-positron pairs, and neutrinos. Most of these particles would have remained within the cloud, but neutrinos would have escaped as they scarcely interact with matter. The other particles would have imparted their energy to the hydrogen and helium, heating the cloud and nurturing star formation and growth. These stars would have taken shape at the hearts of mini-halos, which are early protogalaxies emerging around 200 million years post-Big Bang, prior to the appearance of elements heavier than helium and hydrogen. These mini-halos were primarily composed of dark matter, creating ideal conditions for fueling the birth of these dark stars. This dense collection of dark matter existed solely in the early universe, meaning dark stars could only form in this period of time. These stars, unlike their nuclear fuel counterparts, remained relatively cool and didn't emit the high-energy photons typically associated with stars. This peculiarity allowed them to continually accumulate mass, causing them to expand significantly throughout their lifespans. These stars are somewhat paradoxical. They resemble the Sun in terms of surface temperature but shine with a brightness a billion times greater, rivaling an entire galaxy filled with fusion-powered stars. This theory beautifully explains another mystery that scientists have trouble answering. As these massive dark stars reached the end of their life cycles, they would have imploded into colossal black holes. This could also explain the existence of some ancient supermassive black holes observed in the universe, which appear too large to have formed rapidly from population 3 stars powered by fusion. To seek out these dark stars, the researchers combed through the JWST's catalog of objects dating back to the early universe, nearly 14 billion years ago. Among the limited data on electromagnetic emissions from these objects, only 9 were considered viable candidates. 3 of these closely resembled the characteristics of dark stars. They exhibited a high redshift, indicating aged and distant origins, and they appeared to stem from a singular source like a star rather than a diffuse galaxy. The researchers currently possess only limited observations of these objects, preventing further detailed analysis at this time. A definitive indicator of a dark star's presence would be a distinct feature in the electromagnetic spectrum, where light is absorbed by a specific helium isotope unique to dark stars and absent in normal galaxies. Identifying this signature would require extended observation, a process deemed impractical due to the JWST's high demand for a multitude of astrophysical investigations. However, preliminary findings suggest that if these objects were indeed dark stars, 2 would have a mass roughly 1 million times that of the Sun, while the third would weigh approximately 500,000 times the Sun's mass. The research team is currently working on an automated approach to identify additional dark star candidates, some of which may necessitate less observation time for confirmation. They anticipate discovering many more potential candidates. If they directly observed a dark star, it would be an astonishing feat nonetheless. Alternative methods exist for detecting dark stars, including investigating their signatures within the cosmic microwave background, CMB, a faint radiation glow remaining from the universe's hot early phase. The observation of a dark star would not only unveil fresh insights into the universe's early formation, but also offer a unique opportunity to directly study interactions involving dark matter particles. Observing such interactions would significantly enhance our understanding of dark matter's nature as a particle. While the dark star doesn't change much of what's already established in cosmology, some scientists argued that we were wrong about the age of our universe. The estimated age of our universe could be wrong. When we said that the JWST is changing our understanding of the universe, we weren't exaggerating. We are finding things that are contradictory to our current scientific understanding of the cosmos. We know that the JWST detected highly evolved galaxies just 325 million years after the Big Bang, but these galaxies have prompted a radical hypothesis among cosmologists. One cosmologist is saying that the universe may be twice as old as we thought it was. The current scientific consensus pegs the Big Bang at 13.8 billion years ago, but Professor Rajendra Gupta proposes a revision. He suggests that it's actually 26.7 billion years old. However, another cosmologist employed the Sagan standard, saying that extraordinary claims require extraordinary evidence. So, did Gupta have sufficient evidence to support his claim? To understand his theory, we need to first understand how cosmologists arrived at these numbers. Determining the age of celestial bodies, let alone the universe, is no easy feat. This estimation hinges on observations of the cosmic microwave background radiation and measurements related to the universe's expansion. CMB reaches back merely 300,000 years after the universe's birth. It spread across the cosmos and constitutes the earliest observable radiation. By meticulously analyzing temperature variations within the CMB, cosmologists deduced the universe's age. Hubble's law, established by astronomer Edwin Hubble in the 1920s, contributes to this further. It establishes the connection between galaxies' distances and velocities and assists in determining the rate at which the universe expands. This is known as the Hubble constant. By tracing this expansion backward, we can estimate the time of the Big Bang. In contrast, Gupta's model adopts a radically different perspective. It draws upon the tired light theory, which was initially proposed by physicist Fritz Zwicky in 1929. Gupta uses it to explain the redshifting of photons coming from distant galaxies. Now, remember, redshift arises from the stretching of photons due to the universe's expansion. The tired light theory suggests that photons gradually lose energy as they travel. While this contradicts current observations, Gupta proposes that by letting this theory coexist with the expanding universe, the redshift phenomenon could be reinterpreted as a hybrid phenomenon, not solely due to expansion. The existence of galaxies in the universe's early million years is often termed the impossible early galaxy problem. Scientists have trouble explaining why these ancient galaxies formed so early. Estimating the universe's age faces challenges from physics and observation. Our current knowledge suggests galaxies require time to evolve, accumulating stars and structures through various processes. However, advanced telescopes like JWST have unveiled mature galaxies during the universe's youth, challenging our understanding of galactic formation and evolution over cosmic time. Gupta simply proposes that the universe could be much older than it actually is. To resolve this impossible galaxy problem, Gupta also introduces new variables that change over time. This changes the birth time of early galaxies from 100 million years to several billion years. This leads him to conclude that the universe might be almost 28 billion years old. Scientists are not buying this theory, though. They say that a simpler explanation could be that we don't yet fully grasp how galaxies developed in the early universe. Some even think the impossible galaxy problem is an overstatement. Scientists believe that there are indeed unanswered questions about early galaxy formation in JWST observations, but nothing is inherently impossible. Experts don't see Gupta's theory revolutionizing cosmology anytime soon. Our current understanding of the Big Bang and the universe's expansion is founded on abundant observational evidence and has successfully explained various cosmological phenomena. To gain traction, Gupta's research would likely need further investigation and theoretical development. The standard model of cosmology asserts the Big Bang happened around 13.8 billion years ago. It has relied on measurements from diverse sources, including supernova data, galaxy distribution, and observations of the universe's expansion. Gupta's paper primarily considers supernova data, which is considered insufficient by scientists. Rigorous testing in various ways is necessary. Gupta's theory has garnered significant media attention, though scientists attribute this to irresponsible hype and question the scientific basis of the paper itself. It's important that any contender for the Big Bang's explanation has to account for fundamental cosmological observations. Solving a new puzzle doesn't hold much weight if it can't explain established data. But what do you think? Could Gupta be proven right after more research is done? Or is this another theory that will lose traction as time goes on? As we explore the vast mysteries of the universe, we continually encounter new questions that challenge our current understanding of cosmology. The discoveries made by JWST have opened the door to many previously unexplored areas of the cosmos. In addition to identifying ancient galaxies and potential dark stars, the telescope has also been pivotal in refining our models of the early universe. These observations offer invaluable insights into the formation of the first stars, galaxies, and the role dark matter might have played in shaping the cosmos. One significant aspect of these findings is the possibility that the earliest galaxies might not have evolved in the way traditional models suggest. The discovery of mature galaxies only a few 100 million years after the Big Bang is puzzling to cosmologists. According to current models, galaxies should have required significantly more time to accumulate the necessary mass and structure. However, the discovery of these advanced galaxies raises the possibility that the processes governing galaxy formation may not be fully understood. The notion of dark matter and its interaction with the formation of the first stars could lead to a significant shift in our understanding of the early universe. If dark matter played a role in the birth of stars, it could rewrite much of what we thought we knew about the cosmic timeline. Dark stars, as hypothesized, might have formed from collapsing hydrogen and helium clouds in areas rich in dark matter. This concept could also help explain some of the anomalies surrounding the formation of supermassive black holes.